Machine learning isn't complicated. It's just about mapping outcomes to their causes in a robust programmatic way. Every day we make sentences like, oh, this part is late because the semiconductors are coming from China and that's a messed up supply chain. What we don't realize is by making that sentence, we've actually created the core of a machine learning problem, which is to say, how can we use the destination, the origin, and the type of component to predict whether the part is going to be late or not in our supply chain management systems. Setting up this problem is frequently the most difficult part for teams, and it's actually something that we can break down into 4 straightforward steps. The first is to identify very clearly the outcome you want to happen or maybe avoid. We want customers to buy, we want things to arrive on time, we want to avoid machine failures, we want to avoid customer churn. And in non-business context, this might be as simple as we want to identify what species of bird this is, or we want to detect earthquakes as they're happening or before they happen. The outcome should be measurable, and we should be able to, in historical data, identify when it happens. Then, once we've identified the outcome we want, we can start brainstorming just based on our intuition and our knowledge, the possible hypotheses about what causes that outcome. In the example given before, the type of part. Or maybe in the machine learning model, we would take pictures of birds and it's actually the crown of the bird or the beak of the bird that would have the information about what kind of bird it is. So in either case, we need to turn that hypothesis into a data set. If we're doing the supply chain problem, we need to make sure that our data set has a column for the source of the part, a column for the type of the part. And if we're doing the bird detection example, we need to make sure we have some pictures with both beaks and crowns. Finally, and the most easy step in 2022, plug the dataset into a machine learning model trainer. It's table stakes in this current age of analytic sophistication to have automatic machine learning algorithms that search for and give you the best result back. And so once we've actually identified the cause, the hypotheses in the data set, it should be relatively straightforward to get to an answer. To take a look at this in more detail, we can take examples for 5 different machine learning problems that are highly common in the industry. For instance, customer churn, we want to reduce it. Supply chain delays, avoid it. Customer buying, increase it. Machine breaks down, stop it. Heart attacks happen, prevent it. All of these things are very clear to the person who is in charge of managing it and are also very labelable in data. So as we break down each of these problems, we can take a look at the potential causes of those outcomes. So just taking the first example, a bank customer churns, we sit down with the product team who owns that product, for instance, a checking account, and ask, what are some reasons you think that a customer might leave the bank? Maybe they hold a low balance and it's very easy. They don't direct deposit, they don't use a debit card, they don't use a mobile banking, maybe they don't have a branch nearby. All of these are possible causes of the outcome. We don't know how important they are on a relative basis. We don't know how they interact with each other, but we're pretty confident that the answer lies in some combination of those factors. To use the medical example for a heart attack, if you sit down with a doctor and say this man had a heart attack, they would go through some set of questions. What was their age, their weight, their pre-existing conditions? How was their diet? Are they a smoker? What was their family history and past diagnoses? All of these are very familiar to the person who manages the outcome. And that's why it's actually super important to make sure that the person who is close day to day to the problem we're trying to solve actually pitches in and gives us the hypotheses. So then once we have those hypotheses, maybe we would go and actually assemble the data set. For the churn example, we'd have a data set with customer ID, whether or not they churn, and then all of the columns that we hypothesize. They're balanced, whether they have direct deposit, whether they have a debit card, whether they have mobile banking, their distance to branch. In the heart attack mitigation example, where we want to algorithmically detect disease before it happens, we have patient ID, whether they had a heart attack, And then the weight, the height, the blood pressure, the family history, their triglyceride levels, and all the other things in their blood panel that we can then use to make the prediction. Finally, once that data set's assembled, we can just pull together the variables into a single model and just see what happens. The model might immediately be good enough and we're actually happy. Go home, deploy the model, and we're actually done with the project. Or we see very low accuracy and either we haven't identified the right causes, we need to gather more data, or maybe we kill the project because actually it's not a predictable phenomenon with the data set we already have. To see an example of how easy it is to accomplish step 4 once we have the data set assembled, we can take a look at this example of membership churn from a warehouse store. Think Costco. We know some things about the customer and we know the outcome that we're caring about, whether they cancel their membership with us. We should certainly explore this data set at length, just descriptively. So for instance, we can break down whether or not they cancel store membership by whether they had a store card. And when we normalize this result, we see that those who don't have a store card make up a much larger proportion of those who cancel membership or not. But rather than go through each of the 24 columns one by one, we can easily use an automatic machine learning tool to just combine all the factors and say, what are all the drivers of canceling membership? Now the automatic machine learning tool will abstract away the need to write code, search for the right hyperparameters, etc., and just actually start and quickly return to us a model. The model accuracy is immediately quite high. And we can see that within the model, the top drivers are has a store credit card, total years of customer, age, and number of visits to store. If something jumped out at me as very unintuitive within this, maybe I would go back and look at my data, clean it up a little bit more. If my accuracy was too low, I could always go and gather more attributes about my customer. And if I feel like these all make sense, I could go and sit down with the manager of the loyalty program or the membership program and also make sure that it made sense for them. We can even go down to the individual level and say, we identified some folks who we thought wouldn't churn. These are the factors why. And if I actually showed this person's profile to the owner of the program, they'd probably actually be able to come to the same guess as the machine learning model. They just wouldn't be able to do 100,000 of these people every single second.